Thank you all for coming here today to be part of our monthly Tech Talks. I'm Badri Rajashekar, CTO of TokBox. I'm very happy to have Tom O'Neill from Periscope Data here. Tom is the CTO and co-founder of Periscope Data, and we at TokBox are really ardent sort of customers of Periscope, so I'm very excited to have him here. But the way I came to know Tom was Tom and Jason actually invited me over to their offices where they have this amazing Scotch collection. It is fantastic, and it's also very convenient that they're only like a block away. But that's not what I'm here to talk about. But Tom's going to be talking about data warehouses and sort of how to design your data warehouse, and also in terms of technologies like Redshift and how that impacts the design of the warehouse. So without further ado, I hand it over to you. So, welcome.
Thank you very much. Cool, yes, so tonight we're talking about data warehouses, and the most important thing to realize about a data warehouse is that they are different from regular databases, right? Yes, they're both kinds of databases, but data warehouses are very different. So just a quick show of hands in the room. Who here is a data scientist? Cool, and engineers? And everyone else just loves data, which is great. So cool, so data warehouses are special because the business logic is baked into the schema. Right, when you're running a database, it's going to be behind Node or Django or Rails, and that language has a bunch of code in it to say how your business works. But if you're the data analyst working on your warehouse, there's no Ruby, there's no Node, there's no Django, there's no models, there's no validations, there's no business logic. And so when you're building the warehouse, you have to build into that schema what it means for each column to have a value. And so an example of that is this is part of our schema at Periscope. We have a customers table, we have payment plans, we have subscriptions. And when customers upgrade, we end one subscription and add a new one. If it's an ongoing subscription, the end date is null. Right? So it's pretty great for serving the app. We can show them on a page what their subscriptions are, what they're playing when they upgraded. But it's terrible for analysis. This is a really frustrating schema if you're a data scientist and you want to know how much money did I make in October, or how much money did I make over the course of a year. And so in the analysis database, what you want is a table like this, a customer's plans, where you have the customer. For every month they were a customer, you have what that month's date is and how much money they made. And so this is the kind of change that you want in your data warehouse versus in your serving database. The next major difference is that regular databases, web databases, are made for serving zillions of tiny queries. Right? If you're serving web queries at 10 milliseconds a piece, that's great. 5 milliseconds, even better. 200 millisecond query on your web server is pretty scary. It's going to bring some stuff down. On your warehouse, if you can get a query done in 2 seconds, that's great. Right? You just plowed through 1 billion records and you got to answer in 2 seconds. That's a huge win. And so the numbers are off. So this is our production database. It's running about 130,000 queries per minute as an example. And this is one of our data warehouses. And you can see there's 800 million rows in our production database and 45 billion in one of the warehouses. And that's totally fine because the query volume is just very different. Right? These are all tiny, 10 millisecond queries. These guys down here, these long ones, are us materializing a view or loading in a new table, and that could take a half hour. And that's totally fine. And so because the databases are different, they're optimized for different things. The next major change, scaling your warehouse and scaling your database. So when you scale a normal database, you shard it out. Maybe you shard it by geo, maybe you shard it by product or by customer. And it's the same database serving different queries in parallel. They never serve the same query. Right? The shards are for different things. In a warehouse, you add more worker nodes. And the worker nodes are serving the same queries, but they're working together to do it. And so when the query planner comes in for a data warehouse, it compiles your query into C or C++, and that query gets distributed out over the nodes who all work together on the solution that comes back to the leader node and gets handed back out. Where in sharding, it goes off to one of the databases and comes back. And so that changes how you want to think about your queries and your cluster. Right? So historically, you would scale a data warehouse vertically. Right? Old school data warehouses, you just buy a bigger one. More cores, more RAM, more hard drives. And that worked until 10 years ago when data volumes couldn't be handled by a single box. And so now the industry is obviously going the direction of lots of smaller hardware, lots of cheaper hardware. But that comes with the bandwidth constraint of the network. Right? RAM is 4 gigabytes a second. SSDs are 10th that speed, but still really fast. But when you have a cluster of nodes, they're bound by gigabit network or something a little bit faster. And so that affects queries like this. Right? This is a basic daily active users query. So you have a date, you have count distinct users. This is from one of our tables, time on site logs, which says when our customers are viewing the site. And this query is actually really expensive for a data warehouse, especially a clustered one. Because if you look at the query plan, it's like, all right, we're going to scan the time on site logs table. And that's because like the month of October is on a little bit of every single node, right? This node has some October, this node has some October, and you can't count distinct users across many nodes. You have to get that data all together. And so each node scans and says, OK, on October 1st, I saw these users. On October 2nd, I saw these users. Then the query plan says, all right, node 1, you get the first week of October, and everyone ships their first week of October dates to node 1. Same for node 2, gets the second week, and so on. And once the node has all of the data for each of its dates, it can do a unique count. Right? And so this is very network heavy. Right? There's a ton of network going on here, and this will really slow down your queries. So keep that in mind when you're distributing your data among your warehouse, that what kind of queries you'll run affects how much network you use and how the data is distributed. But all is not lost. Data warehouses have cool things like Approximate count distinct, which is a very different way of counting. If you're willing to take some error into your queries, you can actually count the unique number of elements in a set without communicating between the nodes. And the way that works is with hyperlog-log probabilistic cardinality estimation, which is a really big way of saying using Bloom filters for counting. And so this is a simplified version of that. If you imagine each node builds up a bit set. So for our case, it's daily active users. User IDs are integers. And so if I saw user ID 7 on this first, I have a bit set that goes out at least 7 bits, and the 7th bit is true. And if I also saw user 75 on that same date, now it's 75 bits long, and the 75th bit is true, and the 7th bit is true. And the nodes can do this for each of the dates. And then once they're all done, they send it back to the leader, who just ORs the sets together. Right? And then you can count up the number of true bits. And that will give you the count, the exact count of how many users were seen on each date. The problem is that these are excessively wasteful but in RAM. Right? They eat up a ton of memory. And so hyperlog-log loses a bit of precision, but shrinks those sets down a bunch. So it's just the algorithm is how you have much smaller bit sets, but still get to count up unique sets. Cool. Next major change, relational databases and warehouses store data very differently. So in a relational database like MySQL, the tables are all stored as giant blocks. They're one huge file on the hard drive. So in this case, MySQL, you have 3 columns. They're all together. You can do select star really fast. This is how you can populate profile pages on websites really, really fast. You can say select star from users where ID equals 7. Right? And you shoop, get all of ID 7's rows, or all of ID 7's columns. In a warehouse, you actually store the columns separately. Right? Each column is its own file. It's actually broken into many files. And this way, if I'm like true select star where user ID equals 7, I now have to open up at least 3 files in this case, which is super slow. But if I say I want the minimum date from my table, I can just scan down this column and only open the date. So less I/O means queries go a lot faster. So we can go even further. Now the columns are stored as a single data type in a single file. We can compress them. One type of compression is called run length encoding. And this lets us say, OK, instead of having 12 rows in our table, we'll have 3 rows because there's 4 8-1s, then 6 8-2s, then 2 8-3s. Right? And now our column is just even that much smaller. We can read off the hard drive that much faster. Much less I/O, much faster queries. So going back to that previous example, the reason min date is so slow is that you have to read the whole row in MySQL. Right? You can't just read that last column. And so on the far side there, you see we're reading up, found 8-1, found 8-1 again, found 8-1 again, all the way down to the bottom until we find the minimum date that we're looking for. Where our compressed table, we read 3 rows and we're done. And so that's one of the reasons why warehouses are so much faster for queries like counts and mins than a regular warehouse. Or a regular database. Next major change, indices versus sorting. So one of the benefits of having all of your data in one big table file is you can index it. Right? You can have B trees that say on this pointer is where this row is, where this row is. That works great for regular databases, but it doesn't work for columnar stores. Because columnar stores have their data sharded out over a whole bunch of files. Those same indices don't work. Instead, we sort the data. Right? So sorting the data means I'm going to organize my rows in a certain order. And this way I can look through it. You can look through the blocks and find where the data is you're looking for. So an example of that is in Redshift, you can define a sort key. It's like, all right, I have an events table. It has a created at column. I'm going to say that's going to be how I sort my data. So now on disk, all of Redshift's blocks are sorted by the event time. And when I write a query, like select something from events where created at is greater than the 10th, I can look through each of Redshift's blocks and be like, OK, because the blocks are stored with metadata of what their sorts are, you can say, I'm going to skip this block without even opening it. Right? I already know what's inside this block. Don't need to open it. Don't need to unzip it. Just open it. Skip this one, not this one. Oh, this has dates that are relevant to my query. And so you can just hop through all your blocks to find just the ones that matter. Redshift goes a step further. There's two kinds of sorting in Redshift. There's compound sort keys, which is you have a dominant sort, and then if there are ties, there's secondary sorts, and then interleaved sort keys. And interleaved sort keys will sort of balance the sorting between multiple columns. And this is like, OK, if I'm looking for where user ID equals 2, the left side is much faster. Right? All of user ID's 2 stuff is in the same area, it's in the same block. But on the right-hand side, I have to open up 2 blocks. Right? There are two different files that Redshift has to open up. So if you're optimizing for a very specific query, where you know always what you're going to be sorting by, the compound sort keys are pretty great. But as soon as you sort for something else, like where job ID equals 4, it's no longer looking at user ID, you're looking at job ID. Now you have to open every single block in the left-hand side, because you have no idea where the job ID data is. But in this side, you only have to open half of the blocks, because you're sorting by that some of the time. Cool. 4 common schema patterns that we see with our customers. The first one is the old school, where you have fact and dimension tables. Does anyone have this schema? Do you like that schema? I don't think so. No, it's a terrible schema. So this is great for the old school data warehouses that use indices that aren't columnar, because you have foreign keys everywhere. You just index it all the time with the foreign keys. It's great for not duplicating data, but it's really painful to use in queries because you have like 11 joins in any query you want to do. This one we see a lot. It's just the basic prod REPL. Like, you're the data scientist, and you go to your engineers, and you're like, hey engineers, I want to do some data science, I want to run some analytics queries. You're like, great, here's a read-only REPL, have fun. And that's pretty frustrating because while yes, it's low maintenance and it's pretty easy to use, it comes with no business logic. Right? The database is designed for serving the app, not for serving analysis queries. And so you're on your own to sort of figure out like how everything works and what it means for certain columns to be filled in. If you use a service like Segment or Keen or Amplitude, they'll give you a table like this. So this is a table where any kind of evented service will just stream events to you, and you just write down the whole thing you find. Like, OK, this event was a purchase on this date with this user, with this IP address in this locale. And it's great. It's super simple. Like, anyone can read it and understand what happened. But it's really frustrating for certain kinds of queries. Like, if you want to know what was the last IP address that this user used on the service, that is a brutal query. Because now you need something like a window function over a billion row table to find out what's the last row per user. And that can get pretty expensive. So what we're going for is this thing that looks like Battlestar Galactica. You have your prod database and maybe your external data like Salesforce and maybe your logs. And you put that through some kind of data pipeline that processes it, that builds in that schema, that builds in the business logic, and stuffs it into a warehouse. And so this is great. This is what most folks are heading towards. But it does also have some downsides. Right? There's latency now. Right? The data in your prod database is ahead of the data in your warehouse, because some job needs to push it over. And it requires engineering effort to maintain it. It sometimes is going to break, and you have to like fix the code to get the ETL working. And so with this in mind, we built the Periscope Cache. And so we're trying to automate a lot of the ideas previously in this deck by making something that's super, super fast and easy to use. And so just for context, our cache is built on top of 300 Redshift nodes. And we run over 1 million queries a day, like 1.5 million queries per day on this cache. So it's really high performance, really large clusters of data. At the very simplest level is we just automatically ETL in customers' databases. So Periscope, a user signs up. They want to run charts and dashboards really, really fast. And so we suck in their data, put it into the cache, and we keep their data up to date. And the way we do that is with 3 different strategies that account for most tables like getting updated in the cache. And so if you're building your own ETL pipeline, you probably want to have strategies like this one. So the colors split out a little bit. But on the full side, it's just download the whole table over and over again. Right? Like this is a highly dynamic table, like a user's table. Just download it and stuff it into the cache as often as you want. That's your latency, because there's no way to tell what changed, because the updated at column on the table is probably lying to you. The incremental one is great for logs tables. Right? If you have an event log table that's just adding events, you can just grab the newest rows and toss them into your cache. You can do that as often as you want, and that will make your ETL process super simple for those types of tables. And the last one is great for tables that changed, but only recently. Like if they're roll-up tables showing the past couple days of data, you can, or they're roll-up tables to change the past couple days of data, or they're job tables that mark jobs complete. You can grab the newest rows and update the rows some timestamp back in time. And with these three strategies, you'll be able to build your own ETL pipeline that's super easy and efficient and will work on almost all your tables almost all the time. The next one is when you materialize views in your warehouse, right? You start with your replication of your prod with some data you ingested, but you want to build some logic on top of that. You want to build some views that build in some business logic. What we used to do is have our views build or rebuild every hour, right? Just run the query again, rebuild the view. But it turns out that breaks down once you have a bunch of views. And so what you can do instead, and what we do, is you build a dependency tree of what tables a view depends on and what other views a view depends on. And so as you ETL things into your warehouse, you can see what changed and propagate that change right through. It's like, all right, this view depends on the events table. I just changed the events table. I should rerun this view. And that's much more efficient than running everything on a schedule. And then cross-database joins. When you're bringing things, so we do this when you bring your own databases into your warehouse, put them all into the same database in different schemas. And so we do it by renaming the schemas behind the scenes. And then when a user writes a query, we translate db1.schema1.table1 into our name for that database and schema. This way, you can join your Salesforce data to your prod data. You don't want to have two different Redshift databases. You want them all in the same thing. And then something fun that a lot of our customers are MySQL, and MySQL has some great syntax for certain things. We translate that to the Redshift equivalent so that when you're writing queries, you can still use MySQL syntax, but then have that run on Redshift. And so that's just a sort of a convenience factor that you might want to think about. And so the last bit about the cache that sort of makes it like very useful, and you'll want to build this too when you're building your warehouse, is it is able to fall back. And so for us, we view the origin database, our customer database, as the source of truth. And so when they're running queries, it runs against our cache first, and it runs really, really fast there. But if they want to fall back to the origin database, they can. Right? The query can just get redirected there if they have some exotic syntax the cache doesn't support, or if there's data that's like super recent, like changing every second, and they want to get that. Like you can build your system so that queries can fall back, and that gives you the best of both worlds, where you have the high-performance warehouse and the super recency of the origin database. And the last way we make the cache super, super fast is by having them way over-spec'd. So we have all of our clusters are multi-tenant. And so when a customer joins Periscope, we put them in a cluster with other customers. Right? The data is all partitioned, so they can't see each other's data, but they're sharing the same nodes because no single customer needs the resources of a cluster all the time. And so in this case, we could give each customer a cluster 4x the size they could individually afford. Right? And so from here, we can make things super, super fast. Awesome. That is a whirlwind tour of warehouses. Any questions?
Is kind of architecture common from the mainframe days, or is this something new in the last 10 years?
So Redshift itself was bought, Amazon bought it from another company who built it in the late 90s, I think. And so I think the databases have been stealing ideas for a long time from all kinds of cool tech, but they're like super durable and old. So I would not be surprised if they're one of the first folks to come up with this type of architecture. Cool. Anybody else?
Hey Tom, so when you were talking about schemas, you said like if you just transfer relational database schema into a warehouse, it's not good. Star schema is not good. But when you were talking about glue schema, you pretty much put like data flow chart instead of schema itself. So what about your schema?
Right, so the schema has to have the business logic in it. So if you didn't hear, the question is, if star schema doesn't work and prod REPL doesn't work, like what is the schema you want in your warehouse? And like the example in the beginning of the deck, like we have the subscriptions table and the customers table and the plans table. If those are hard to work with because they're meant for serving, like smash them into a different shape. That is great to work with for analysis. Like, okay, you're doing a ton of revenue analysis, then great, let's build a table so that they're easy to do revenue charts on. Did that answer your question? Cool.
So you have to.
Go ahead.
So you have to change your schema whenever you do analysis.
So you have to have the flexibility in your system to be able to make new schemas on the fly, right? And so you have the heavyweight tables that are just coming from prod are always coming in, and then on top of that, you'll want a layer that's like, okay, materialize these three tables in this way. And then if you change it, you're like, okay, change my view script and materialize it this way now.
Cool.
Yeah, so that is actually the hardest problem. Like getting the data is super easy, but keeping it in sync is super hard. And so we have a bunch of checks that run in the background to make sure the tables are the same. And then when any of those checks fail, we just download the whole table again.
You had given the example of date, which has like 365 different values. It's easier to compress, but how do you do it with strings?
So for strings, Redshift uses LZO compression. Redshift uses LZO. You just zip it up. Because it's easier to read a compressed blob off the hard drive and unzip it than it is to read like a decompressed blob. It just takes less time. And so the smaller you can make the data on disk, the faster you can read it.
Yeah, but I've read about different compression algorithms for strings also.
Sure.
Like names, they are like 600,000 different kind of names, and then there's combination and variations. And there are such things. Yeah, you guys don't use those.
So one of the cool parts about Redshift is when you're loading your data, it will pick compression for you. And so if you have a string column with low cardinality, like it's mostly the same value or only like several hundred values, it will not pick LZO, it'll pick something else. Like it'll pick an enumerated type compression.
Yeah, but then what? It's picking a wrong compression.
So worst case, the column will be larger than if it was raw. Right? Like it'll pick a
You don't have any choice, but they have whatever they choose, you have to use it.
You can change it. Yep, you can let them pick it, or you can set it yourself, depending on what you like. If you think you know more about the data and their sample is wrong, then you can definitely change it.
So you said your queries may fall back to original database.
Yes.
Right? The original has the OTP kind of schema, and the query calls like the normalized schema. So the same query cannot be executed on both databases, right?
So in Periscope, the way we define our views is that they're defined as SQL, like SQL selects. And so if they can't run on the warehouse, those views are replaced with inline selects and sent back to the origin database. And so this way, the SQL that's being run on the warehouse and the SQL that's run on the database are very similar.
In your diagram, when you had the ETL box,
Yeah.
are you really transforming the data, or is it just really all views?
In the warehouse design, right? So most of the time, it's just shepherding it through, right? Changing types, guessing schemas, guessing compressions. Sometimes the data needs to be converted a little bit to fit in the warehouse shape. But most of the time, you just want to get an exact copy into the warehouse.
Okay, so it's not the traditional classical ETL where it's heavy transformations?
No.
Okay.
Yeah, you want as light as possible into the warehouse and then do the heavy transformations once there. Because you have the much more flexibility in the warehouse to do transformations on the fly.
Oh, so everything's dynamic?
Yeah.
All views, heavy views?
So we materialize the views into real tables.
Okay.
But we do that in the warehouse so that if you change it, we can just do it right again right away.
Okay.
Cool.
So do you have any joins at all in your warehouse? And do you have primary keys and foreign keys?
So the warehouse has dist keys, so how the data is split up among each node, and the warehouse has sort keys. But foreign keys and primary keys don't really work so well in a schema that can't be indexed.
So did you actually specifically have problems with foreign keys?
Nope. Nope. It's been working out pretty well so far. Cool. Anybody else?
When you were designing the architecture of your system,
Yeah.
what were some of the technologies you used and why Redshift? It's a great system, but what was that discussion like?
Yeah, so we had this giant spreadsheet. We tried a whole bunch of things. It took us a week or two to try I think a dozen different vendors. And we found another one that was pretty fast on a really narrow set of queries. And we're like, oh, this is going to be the one. And then it was so difficult to maintain. It was not going to be worth the ops cost. And Redshift was almost as fast and just came for free, right? No ops cost. The clusters just work. Oh, you want more nodes? Press the more nodes button, and it's just bigger and faster now. And so with the trade-off of it's almost as fast and super easy to maintain, Redshift for us was the obvious winner.
Can you name this second choice?
It was Vector. Vector. So
Is it cloud-based?
what?
Cloud-based?
No. It was you install it on your own hardware, but it uses by its name vector operations from the processor, and so you can do certain kinds of queries much faster because it will use the vector operations.
So, another question now. How do you keep track of the data types and the columns in terms of the data model versus your
Yes, so the question is, how do we translate the schema types from one to the other? It's a giant mapping table, right? So MySQL and SQL Server and Postgres have types that aren't supported in Redshift. And so we just have a list of, if you're this type, go to this one. If you're this type, go to this one. And
do you have them for each of the database, so like SQL Server,
Yep.
SQL, Postgres?
Yep. And then some databases allow user-defined types. And in general, we just default those to strings or to varchars.
Did you compare it with Vertica? Can you compare it with Vertica?
Yeah, so Vertica is super cool. At the time we tried it, they didn't have a cloud option, so it was self-hosted. What they do that is sort of unique to them is projections, right? And so Redshift, you can sort your data in one way or interleave with just like 2 ways. And that's great. That works out very well. But with Vertica, you can have projections, which is like you can sort it this way and sort it this way, and it doubles the amount of data you have, but the data is organized in a way that'll be much faster. So depending on your needs and how much I/O capacity you have, that can work out really well.
Can you just say a few words about how your ETL process works? Like, do you have some staging database where you discover everything and then process it?
How we ETL?
Yeah.
Yeah, so we have a Go server that's whole job in life is to just download data from customer databases. It stores it in S3, and then from S3 we load it into temporary tables or into staging tables in Redshift. And then once those tables are like good to go, we'll drop the old one and rename the staging table to the real name.
So how do you handle crash in the pipeline? Like the ETL server is the server and the crash in the middle?
All the jobs are, well, the jobs aren't restartable, unfortunately, but they are cancelable. Right? We know that we left off at this point, and so it's like, okay, we're going to try that again from that over. And so we do lose time, right? If we just lose a database connection, we can't recover that. But we do know where we are, and part of the process is always to compare what we have versus what we want. And so it's like we don't sort of guess that we have these rows in the cache. It's like, what do we actually have in the cache versus what do we want? Cool. Well, thanks, everybody. It was super fun. I hope it was helpful.